Problem 6. Using the data presented in this figure, determine the number of free electrons per atom for intrinsic germanium and silicon at room temperature 298 Kelvin. The densities of germanium and silicon are 5.32 and 2.33 gram per cubic centimeter respectively. The atomic weights of germanium and silicon are 72.64 and 28.09 gram per mole. Explain the difference in these free electron per atom values. Okay, first of all, we need to find the free electrons per cubic meter in both germanium and silicon. Since germanium and silicon are semiconductors, their free electrons at various temperatures can be found from this figure. So in this figure, on the x-axis there is this temperature, and on the y-axis is called the intrinsic carrier concentration, which is the same as the free electrons in the metals. So if you draw a line at 300 Kelvin, okay, and then this line, vertical line, will intersect the silicon and germanium curves at these 2 points. So you can read the values of these concentration at these points. So I can read these values as like for germanium, okay, so germanium, you can read this value as something like N germanium, okay, is equal to 5 into 10 to the power 19. So you can see that it's somewhere here. This value is somewhere here, and the other value is from somewhere here. So it will be about 7 into 10 to the power 16 for silicon. So for silicon it will be 7 into 10 to the power 16. So when now we need to find the total number of atoms. So these are the electrons. These are kind of free electrons. Free electrons. Okay, how many number of atoms are here? So we can find from this equation Avogadro's number, and then this is density. So let's see first. Find for germanium. The density of germanium is 5.32, and atomic weight of germanium is 72.64. So this equation will give us the number of atoms per cubic centimeter. So if you multiply it with 10 to the power 6, it will be number of atoms per cubic meter. So this is also per cubic meter, okay, per cubic meter, and this is also per cubic meter. So we will find this. And similarly for silicon, 6.022 into 10 to the power 23 into 2.33 divided by 28.09. So I am going to calculate these two values. So the number of germanium atoms are 4.41 into 10 to the power 28 per cubic meter, and this is equal to 4.99 into 10 to the power 28 per cubic meter. So now we can see the difference. Okay, number of the ratio 5 for the number of germanium electrons divided by number of germanium atoms. It is, the ratio is 5 into 10 to the power 19 divided by 4.41 into 10 to the power 28, and this will be some ratio. The other ratio will be for number of silicon electrons, free silicon electrons divided by the number of free silicon atoms. So this will be 7 into 10 to the power 16 divided by 4.99 into 10 to the power 28. So I will calculate it. Okay, so this will be 1.13 into 10 to the power minus 12. Yes, sorry, this will be 1.13 into 10 to the power minus 9, and this will be 1.4 into 10 to the power minus 12. Okay, so electrons per atom. So as you can see that this ratio for germanium is much significantly higher than silicon. So the difference between these two ratios is that the band energy in silicon is greater than in germanium. So it is difficult for the electrons in the silicon to move, and to behave as more free electrons compared with germanium. Problem 7. At room temperature, the electrical conductivity of lead delinium is 500 ohm meter inverse, whereas the electron and hole mobility are 0.16 and 0.075 meter square per volt second respectively. Compute the intrinsic carrier concentration for lead delinium at room temperature. So well, for this question, when we have the electron and as well as the hole mobilities, so we can use this equation for finding the intrinsic carrier concentration, which is basically the used for the free electrons per cubic meter, okay, in the case of semiconductors. Okay, so sigma, that is the conductivity, it is equal to 500 equal to Ni. Ni is intrinsic carrier concentration. Okay, so it is Ni. Ni is one term multiplied by the charge of electron, 1.602 into 10 to the power minus 19 coulomb, multiplied by 0.16 the electron mobility, and 0.075 the hole mobility. So in this case, the intrinsic concentration will be calculated to be 1.33 into 10 to the power 22 per cubic meter. Okay, so problem 8. An N-type semiconductor is known to have an electron concentration of 3 into 10 to the power 18 per cubic meter if the electron drift velocity is 100 meter per second in an electric field of 500 volt per second. Calculate the conductivity of this material. Okay, so in this case we have been given an electron concentration of 3 into 10 to the power 18 per cubic meter. Drift velocity is given, and electric field has been given as 500 volt meters. So from this we can find the value of the mobility, okay, electron mobility from this equation. So Vd is equal to 100 drift velocity is 100 meter per second. Mu E is the electron mobility multiplied by the electric field intensity, which is 500 volt per meter. So mu E is equal to 100 divided by 500, which will be equal to 0.2 meter square per volt second. And using the second equation, with which we can find the conductivity, which is equal to now n. N is the electron concentration. Okay, 3 into 10 to the power 18 per cubic meter. 3 into 10 to the power 18 cubic meter per cubic meter, and multiplied by 1.602 into 10 to the power minus 19 coulombs, multiplied by this value which we have just found. So this will be calculated out to be 0.096 ohm per ohm meter. 0.0969612 ohm meter inverse.